Imagine a sunny afternoon at the park. The sky is clear, the sun is shining brightly, and the air is filled with the sounds of laughter and joy. Two children, a giggling 6-year-old girl and her older brother, are playing on a trampoline, their faces lit up with excitement and fun. The little girl bounces high, her laughter echoing in the air, each jump taking her closer to the sky. Her brother, barely leaving the trampoline's surface, watches with a smirk, his eyes following her every move. "You're bouncing so high because I'm pushing down on the trampoline," he teases, convinced of his own cleverness and the logic behind his statement. After all, isn't that how it works? Doesn't his weight pushing down make her bounce higher? This playful scene highlights a common misunderstanding of Newton's third law, a principle that governs much of the physical world. It seems intuitive that the brother's weight is the primary force propelling his sister upwards, a simple cause and effect. However, this explanation overlooks a crucial element of the equation, the trampoline itself, a dynamic and responsive surface. The trampoline isn't just a passive platform, it's an active participant in this game of forces, storing and releasing energy with each bounce. This misunderstanding, though common, misses the elegant symmetry at the heart of Newton's third law. For every action, there is an equal and opposite reaction, a fundamental truth of physics. The brother isn't pushing his sister up, he's pushing the trampoline down, applying force to the surface. The trampoline in turn pushes back with an equal and opposite force, propelling the sister into the air with a burst of energy. It's a dance of forces, a delicate balance between action and reaction, where each movement is met with a counter-movement. This simple yet profound interaction on the trampoline is a perfect illustration of the principles that govern our world, a reminder of the unseen forces at play in our everyday lives. Sir Isaac Newton, a towering figure of the scientific revolution, gifted us with this profound insight. For every action, there is an equal and opposite reaction. This principle, though seemingly simple, has far-reaching implications that extend beyond the realm of physics. This simple statement, known as Newton's third law of motion, has revolutionized our understanding of the universe. It is a cornerstone of classical mechanics and has paved the way for countless scientific advancements. It's a law that governs the motion of planets in their orbits, the flight of birds in the air, and even the simple act of walking. Every movement we make and every interaction we observe is a testament to this fundamental law.
Let's break down this law with a simple example. Walking. When you walk, you might not realize it, but you are constantly engaging in a dance of forces. When you walk, you push back against the ground with your foot. What happens next? This push is the action. The ground pushes back on your foot with an equal and opposite force, propelling you forward. This pushback from the ground is the reaction. This exchange of forces, this push and pull, is the essence of Newton's third law. It is a dynamic interplay that is constantly at work in our daily lives.
Think of a rocket launching into space. The principles of action and reaction are vividly demonstrated in this powerful event. The rocket expels hot gas out of its engines, the action. This expulsion is a force directed downwards. In return, the gas exerts an equal and opposite force, pushing the rocket upwards, the reaction. This reaction force is what propels the rocket into the sky and beyond. This principle of action and reaction is fundamental to our understanding of motion, from the smallest particles to the largest celestial bodies. It is a universal truth that connects the microcosm with the macrocosm, illustrating the interconnectedness of all things in the universe.
Newton's third law, first published in his groundbreaking work Philosophiae Naturalis Principia Mathematica in 1687, wasn't just a scientific breakthrough, it was a paradigm shift. It provided a unified framework for understanding motion, connecting the terrestrial and celestial realms. No longer were the heavens governed by different laws than those on Earth. Newton's laws applied everywhere, from the falling apple to the orbiting moon.
This newfound understanding paved the way for countless technological advancements. Engineers used Newton's laws to design bridges, buildings, and machines. Architects relied on his principles to create structures that could withstand the test of time. Newton's third law wasn't just an abstract concept confined to textbooks. It was a practical tool that shaped the world around us.
Despite its elegance and simplicity, Newton's third law is often misunderstood, sometimes with disastrous consequences. This fundamental principle, which states that for every action, there is an equal and opposite reaction, is a cornerstone of classical mechanics, yet its misinterpretation can lead to severe engineering failures. Take, for example, the infamous collapse of the Tacoma Narrows Bridge in 1940. This event is one of the most dramatic illustrations of what can go wrong when the forces at play are not fully understood or properly accounted for. This engineering marvel, once dubbed Galloping Gertie for its unsettling tendency to sway in the wind, became a cautionary tale about the importance of understanding forces. The bridge's dramatic movements were not just a curiosity, they were a sign of underlying issues that would eventually lead to its downfall.
While multiple factors contributed to the bridge's demise, a crucial element was the failure to fully account for the aerodynamic forces acting upon it. Engineers at the time did not fully grasp how the wind would interact with the bridge's structure, leading to catastrophic results. The wind, pushing against the bridge's surface, generated lift and turbulence. These aerodynamic forces were not just minor annoyances, they played a significant role in the bridge's eventual collapse. This force, coupled with the bridge's inherent design flaws, created a resonance effect, amplifying the oscillations until the structure could no longer withstand the strain. The bridge's materials and design were simply not equipped to handle the dynamic forces at play.
The Tacoma Narrows Bridge serves as a stark reminder. A flawed understanding of the interplay between forces can have catastrophic consequences. The wreckage of the bridge stands as a testament to the importance of thorough engineering analysis and the dangers of underestimating natural forces. It underscores the importance of rigorous testing, meticulous design, and a deep appreciation for the laws of physics. Engineers and designers must always be vigilant, ensuring that every aspect of a structure is scrutinized and tested to prevent such disasters from occurring again. The good news is that we're making progress in combating these misconceptions. Educators are employing innovative approaches to teaching physics, moving away from rote memorization and towards a deeper understanding of fundamental concepts.
Interactive simulations, hands-on experiments, and real-world examples are breathing new life into the study of physics, making it more engaging and accessible. The goal is to empower students to think like scientists, to question, explore, and discover the laws governing the universe for themselves.
By fostering a love of learning and a thirst for knowledge, we can inspire the next generation of scientists, engineers, and innovators. Newton's third law, while a cornerstone of classical mechanics, isn't the final word on the universe's workings. Albert Einstein, in his theory of general relativity, expanded our understanding of gravity, describing it not as a force but rather as a curvature of space-time caused by mass and energy.
Yet even within the framework of Einstein's revolutionary theory, the principle of action and reaction finds its place. The curvature of space-time caused by one object influences the motion of other objects. Action and reaction, though manifesting in a more complex manner, remain fundamental to our understanding of the cosmos.
The universe is an endless tapestry of wonder, brimming with mysteries waiting to be unraveled. Newton's third law, a testament to the power of human curiosity and ingenuity, offers a glimpse into the elegant laws governing our world and beyond. So, the next time you see a rocket soaring through the sky, a bridge spanning a mighty river, or even just a child bouncing on a trampoline, remember the intricate dance of forces at play. Remember Newton's third law: for every action, there is an equal and opposite reaction. And never stop questioning, exploring, and marveling at the universe's boundless wonders.